net zero, and what does it mean? You hear this term all the time, and so net zero, when we're talking about that, you hear politicians talking about that, we're really talking about emissions, and we're talking about balancing the net emissions that we put out into the atmosphere from, manufacturing, energy production, land use patterns, all that kind of stuff, balancing that with how much carbon we're sequestering at the same time, right? We're trying to get climate change under control, and so net zero, we're talking about carbon emissions. And so all of this is driven because the International or Intergovernmental Panel for Climate Change, and they've known this for like 25 years, what this looks like, but they've known that to kind of get climate change under control, we have to keep global temperatures within that 1.5 degree overall increase. And so this is the number, and this is the science that's driving all of our regulations and policies. And we need to get about 50% of the way to net zero emissions by 2030 and net zero by 2050. So this is what our federal government regulations and policies are striving towards, and this is what BC is chasing as well. There's a couple things that add together towards getting to net zero from emissions. There's embodied carbon. We're going to talk about embodied carbon today, and that is the emissions associated with the materials of construction. I'm talking about buildings here, so it's materials and operation of those buildings over its life cycle, from extracting materials from the ground to using them and replacing things over the life cycle of the building to end of life material recovery. Operational carbon is emissions related to energy. So that's your energy use and the emissions associated with that. And then to get to net zero, we're trying to avoid emissions too. So we'll start to see more about renewable energy generation and maybe buying carbon offsets or things off-site. So that's kind of our package for buildings to get to net zero. So here's a quick poll for you guys. What do you think contributes more emissions in BC every year? Is it the emissions from all the new buildings that we're building every year, new construction as well as retrofits of existing buildings? Or is it emissions from energy use of our entire building portfolio? They're almost identical. So embodied carbon from new construction and building renovations every year in British Columbia, 7.2 megatons. Operational carbon from energy signatures, in the province is 8.3 megatons. So the step code and the zero carbon step code or building codes are really only focusing here right now. Key things to remember: embodied carbon is the emissions from the materials in the building, and operational carbon is emission from energy use. Achieving zero carbon requires us to tackle both of those. And then whatever we can't reduce is we need to buy offsets, right? So let's quickly look at the regulatory context and kind of what's happening. So, the feds have standards. The federal government has a 2030 emission reduction plan for Canada, where it assigns responsibilities across the provinces, and it also assigns responsibility to buildings that you guys are responsible for. Clean BC has a roadmap to 2030. And both of these plans are, they have acts underpinning them. So they are regulation. We have to hit these targets. We have to report and measure on this every year. And that's why the regulators and the utilities are pushing back on you guys to deliver savings. So how are we going to get there? So here's 2020 and here's 2050. I didn't make this up. This is from the Canadian Institute for Climate Choices. But we've got to see this reduction in emissions. And in here are the solutions that are going to get us there. And so the little blue dots, or the greeny blue dots, are the safe solutions, are the things that we know we have those technologies today. We can start deploying them right away. And the orange dots are the things that are emerging technologies and solutions. So we don't know how we're going to get, today we don't really know exactly how we're going to get to net zero at 2050, right? But we're working on it. So what do those solutions look like? So the big bubbles on getting to 2030, heat pumps, clean electricity, energy efficient equipment, renewable natural gas, fuel switching. That's what makes up these blue dots in here. That's the majority of our savings, and that's all the stuff you guys are responsible for. So in 2050, that's where, we start seeing a lot more of these orange dots appear. And I haven't illuminated them, but this is carbon sequestration, right? Carbon capture and storage. These are technologies that we're developing, and they're not there yet. And so if you think about the pathway to 2050, they're going to do all the stuff that we know right away, and that's where buildings fall in. And that's why the pathway to decarbonize buildings is faster than 2050, and that's why it's more aggressive. Clean BC has a section for better buildings. They're targeting, the 2030 Clean BC plan is targeting 59 to 64% emission reductions from buildings and communities. So there's some land use in there in that target. 5 big areas where they're focusing on seeing those reductions, and that's what's driving the policies, the incentive programs, the step code, the zero carbon step code that you're already seeing. So they're tackling, energy efficiency, low carbon energy sources. Down here at the bottom, they say low embodied carbon materials, but we don't have any regulations around this yet. Does everybody know what the step code is? Yes, you're a winner. Step code for Part 9 buildings, which is what I was going to focus on today, is in 9.36 of the building code. May 2023, this became mandatory for all municipalities everywhere in the province. Step 3 was required. And Step 3 is about a 20% efficiency improvement over the previous code. In May, we also adopted the zero carbon step code. And I'm going to talk to you about this because zero carbon sounds a lot like no natural gas, and that's not actually what it means. But we'll talk about this a little bit later. But the zero carbon step code is an optional pathway. Municipalities choose what they want you to achieve, right, based on their greenhouse gas reduction targets. Important to keep an eye on is 2027. That's when the step code ratchets up again, and we're looking at buildings that are 40% more efficient. So if you're doing load calcs on buildings, expect those load calcs to be looking at different envelope details and higher performance targets by 2027 or sooner. If you're in the Lower Mainland, a lot of municipalities have adopted that sooner. 2032, is the end of, remember how I said, on our pathway to 2050, the sure bets, buildings have a lot of sure bets in terms of decarbonizing. So we're trying to decarbonize buildings faster. So 2032, we're at the top step of the step code for Part 9, roughly 80% more efficient buildings. By 2030, Clean BC says we're going to have more efficient equipment. Every new piece of space or water heating equipment will be at least 100% efficient. So that's a big change for us. And we're waiting to see that roll out, but that's going to mean we're going to have problems with fossil fuel combustion equipment. So before I wrap up the conversation about regulations, I think it's really important to be clear about what the BC Building Code means when it says net zero energy ready. So a net zero building is a building that produces as much clean energy on site as it consumes in a year. It doesn't mean you're disconnected from the grid, but it means that you have, solar panels on the roof and your EnerGuide label says you're down here at zero. You're certainly consuming energy. If you're familiar with these labels, it tells you, this much for heating, this much for ventilation, this much for lighting. But you're producing it net over the year with that solar array to bring it down to zero. CHBA manages a net zero labeling program, so you may be used to seeing their net zero home label. The BC Energy Step Code, with their 80% more efficient buildings at the top step, is striving to build a net zero energy ready building. So the buildings we're building by 2032 or probably sooner are going to be so efficient that they can generate enough power on site to meet their energy needs net over the year. So quick recap, Clean BC, they're asking us by 2030, 59 to 64% efficiency or emission reductions from operational and embodied carbon. But if we're not measuring embodied carbon, they're expecting you to deliver that from from operational emissions. Operational carbon is the only thing in the BC building code, right? There's nothing about embodied carbon in the building code. And operational carbon is called the zero carbon step code. It's 9.37. And embodied carbon is not regulated yet. Okay, so what does this mean for envelopes? So how are we getting to that net zero energy ready envelope? On average, for a home, a residential building, 60% of the energy use of that building goes for heating and cooling. That includes domestic hot water use. And so in BC, a lot of our emissions are linked to that heating energy because we do a lot of heating with natural gas. What we're moving towards in the BC Energy Step Code is buildings or homes that look like this, that, they've got a thin line, not very well insulated envelope. There's holes around for air leakage. And, we've got a large mechanical system. As we move across on our pathway to 2032, we're tightening up that envelope, which shrinks the mechanicals, and then we're adding a lot of insulation and efficient enclosure details to really further shrink that mechanical system. So much smaller systems, and those buildings have different problems or different opportunities as well. So the design teams working on these projects are working with 6 principles in mind. 4 of those principles have to do with the building enclosure, and the last 2 over here about ventilation and mechanicals are around the scope of work you do. So hopefully the design teams are working with you to come up with the best combination of options to hit the requirements of the STEP code. So the STEP code is now a performance-based code, and every building is energy modeled. For Part 9 buildings, that's generally HOT 2000 software. You have an energy advisor typically who builds that model. They program in, how much windows you have, similar to your load calcs for TECA, but then we simulate that over the normalized weather file and figure out exactly how much energy that building should use. This is the same thing that we've done for years to generate those EnerGuide labels, but we're doing them to prove STEP code compliance, and we're doing those for a building permit stage. So at the time when we get a building permit, we know all the details of the building. We know the mechanicals that are going in, we know the window spec, everything is pre-approved, and any changes to that have to get modeled and updated and get an updated confirmation that your building will comply. So under the STEP code for Part 9, there are 3 metrics you have to comply with. It used to just be, you put in efficient equipment that was this efficient and you built an air barrier and you were good to go. With a performance-based code, that computer model is going to spit out information based on what you input in the design on the envelope, air tightness, and mechanical systems. So there's 2 metrics, TEDI and ACH, and those are the ones that are linked to the building envelope. And the last one we'll talk about a little bit later is linked to the mechanical systems that need to support that building envelope and the occupants. When the STEP code talks about TEDI, it's in kilowatt hours per meter square per year. So there is a limit of energy that building envelope can use in a year. It's not a BTUH number, it's a BTU consumed net over the year type number. So nobody cares how big your equipment is under the STEP code. They just care how much it uses over the year to heat that building or to deliver the energy needed to that building. So that's what TEDI is. Air changes per hour is a measurement of air tightness, and air changes is really interesting because it's the first time we actually go out and evaluate performance of your system. In a past life, I went out and evaluated the performance of mechanical electrical systems in green buildings, and they never performed the way we expected. And so we're not trying to, go and measure how much energy your building is using, but with air tightness, we measure that. And so that's the piece that if anything falls down or falls apart during construction, you don't hit that air tightness performance measure. So a reminder, those 2 metrics around, 2 of the 3 metrics focus on the building envelope, and they lead us to do that envelope first approach. If you remember that icon where we are plugging up the holes in the building, making the walls thicker before we deal with mechanical mechanical electricals, that's called an envelope first approach. That's required with STEP code. So what does that net zero energy ready envelope look like? So it's a high performance envelope. We know we need to reduce energy by 80% in these buildings, so we've got to tackle the envelope first. 4 big areas. Remember, we talked about 4 of the 6 principles were linked to the envelope. The first one is the improved air barrier. So you can see this red line around the house. That's that air barrier, that continuous air barrier detail. We'll see more insulation. We'll see reduced thermal bridging. I'll talk a little bit about that. Better windows and doors, right? So not anything that's surprising. But air tightness is an important one to spend a bit of time talking about. Why are we so focused on air tightness? There's energy linked to air tightness, there's moisture issues linked to air tightness, and there's comfort of occupants. You remember you're inputting air tightness over here. You remember you're getting, on your heating load side, you're getting, some specific demand loads. You're understanding what percentage of that heating load is linked to air leakage and infiltration, right? So it's for sure in there, and you can play around next time you're doing a heat loss, heat gain calc, change some of those air tightness numbers and see what kind of an impact it makes on your load, because it's significant. So ACH, or air changes per hour, has the potential to double the energy used annually. It's not going to double your load calc on your TECA, heat loss, heat gain, because that's your peak, that's the sizing of your equipment, but net over the year, that energy is being lost all the time, right? And so that can have a huge impact on how much energy your building consumes. There's a lot of risks associated with air leakage in a building enclosure. This is a 4x8 sheet of drywall, no vapor barrier on it. But it's exposed to the indoor environment in your house, right? So 50% relative humidity, or that one's 40% relative humidity, 20 degrees Celsius indoor air conditions. And so over a heating season, about 1/3 of a liter of water can diffuse from the air around us, because we're breathing and cooking and showering and that kind of stuff. And it can diffuse into the wall cavity, right? It's going to move because vapor travels from areas of high concentration and warm areas to areas of low concentration and colder air. So vapor drive in a heating dominated climate is from the inside to the outside. So vapor in our house is always trying to drive out and into the wall towards the outdoors. So over a heating season, 1/3 of a liter of water can move through that wall if I don't have vapor control. Air leakage in a 1-inch hole can introduce 90 times as much water. 30 liters of water can come into my wall assembly from the air around us over a heating season. So this is a huge, huge difference. So the focus on air tightness and the focus on measuring air tightness and making sure we don't make mistakes is because there's a huge building science, risk associated with air leakage. Air barrier. The poly, if you haven't, done a drywall repair lately, is generally right behind the drywall. And the poly is generally, typically in buildings, it's the vapor barrier that has to be on that warm side of the building to keep all that moisture from driving into the wall. And it's often used as an air barrier. But you could start seeing wall assemblies where your poly is only acting as a vapor barrier, and the outside, the building paper, the Tyvek, becomes your air barrier. Tyvek, you can see this is your framing cavity. We're seeing with the STEP code, we're going to see more insulation. So once you start adding exterior insulation, then you're really protecting that air barrier. So your air barrier can be on the inside, it can be on the outside, it can be sandwiched between some layers of insulation. As long as it's continuous, it's effective. It doesn't matter where it is. In a deep, fat wall like this, we want 2 air barriers. You guys don't need to figure this out, but somebody in your project team should tell you exactly what materials are the air barriers. Is it on the inside? Is it on the outside? What is the strategy to detail that air barrier? So you have to understand what each of these layers are doing. Where's your air barrier? Where's your vapor barrier? So the air barrier needs to be sealed and made continuous, and the vapor barrier just needs to be everywhere, but it doesn't need to be made airtight unless your vapor barrier is also your air barrier. And a lot of our old buildings, poly behind the drywall was the air barrier and the vapor barrier. And more people are shifting to an exterior air barrier, using your Tyvek as the air barrier, because it's easier to protect over the life of the building, right? When you want to put in a new kitchen, there isn't all this damage to your air barrier. But it's also, there's fewer interfaces to manage. Fewer trades are working in that zone. As we make the walls thicker, we're adding in higher performance windows. We're also getting a little bit more scared about building science in these homes. And I say scared, I get scared because what happens is, as we add more insulation, the drying potential of those assemblies, like I was pushing a lot of heat through the walls, right? All those PTUs in that furnace were pushing heat through the walls to dry it. So if I was having some condensation from air leakage in my wall, it was probably okay in my 1950 home with 2x4 walls, because I was pushing a lot of heat through to help keep it dry. But as I make those walls really thick, there's almost no heat getting through those walls anymore. So the drying potential has decreased. So we're seeing a shift to things that are less risky from a building science perspective, right? We're trying to mitigate condensation on windows. This is some condensation in a basement, because there's moisture inside the construction cavity, and this is poly. So the moisture is condensing on the poly because the basement's cold, and we've got too much moisture in the wall assembly. This is probably an area where, there's some cold surfaces, probably in a basement as well, but poor air circulation and really high indoor relative humidity, where moisture could condense and mold could start to grow. So there's a lot of concerns, and that's why you will see, I'm already hearing, building officials saying this is too risky. We want to see, a building, enclosure specialist and engineer sign off on this detail. They're worried about moisture and that kind of thing. So it's a good time to go back and look at vapor barriers when we're talking about moisture. You can have vapor barriers and vapor retarders. By code, you have to have something on the warm side of your assembly that is going to prevent moisture from migrating into the wall assembly. In the building code, they generally call that a vapor barrier. And the vapor barrier that we're super familiar with is poly. So they have to be on the warm side of the assembly. In a building that's heated. They have to be continuous, but not necessarily airtight. So that's why it's good to know which one is your air barrier. Because they're not so worried about you putting, penetrations through a poly, making sure they're really airtight if poly is not the air barrier, right? And it's the Tyvek, like you mentioned. So knowing where to make those airtight connections is important. A new emerging thing that we're seeing is, I guess it's not really new, but smart vapor retarders. So if you think about your Gore-Tex coat or something like that that's going to allow you to dry, smart vapor retarders are kind of like that. If there's moisture in the wall and high humidity levels in your wall assembly, it'll let that moisture dry to the inside. But all that warm, moist air in your house, it's going to prevent it from migrating into your wall assembly. So I'm hearing, building officials saying, below grade, basement walls, nothing but smart vapor retarders. We're not letting them put poly below grade because we know we're going to see condensation down there, especially, if the footings aren't wrapped, right? The concrete is constantly pulling moisture up and bringing that inside. So we're seeing, changes around vapor control materials. Those highly insulated assemblies, which I mentioned, are changing what we do. So if this is, you imagine this is your inside air at 20 degrees Celsius, 50% relative humidity. The dew point of that air is 9 degrees. So if it's minus 20 outside and you just had your regular 2x6 wall with batt insulation, probably the plywood sheathing would be at the dew point, right? It would be at minus 20. Right, so somewhere in here, any air leakage can condense, right? Any moisture that's in there can condense and cause rotting. As you add insulation to your wall, especially if it's like in this picture where it's on the outside, so that's rigid continuous insulation on the outside, you're warming up the temperature of that sheathing. Probably it's not below 9 degrees anymore, right? So we're now building a more durable and resilient building enclosure by, it can't dry as well because there's not as much heat moving through that wall, but we're keeping anything organic above the dew point. So we're going to see some focus on this kind of stuff, right? Doing things that are less risky. So some of the solutions you're going to see in walls is these fat walls, especially split insulated walls. So you've got something maybe in the cavity, but you've got continuous insulation on the outside, reduced air leakage, vapor permeable insulation. So like rock wool insulation on the outside of your building enclosure, rock wool is like more permeable than Tyvek. So Tyvek is like a Gore-Tex coat, lets things dry, and rock wool is even more like that mineral wool insulation, the rigid stuff is more permeable than the Tyvek, right? So really durable building enclosure if you do that. So as the walls get thicker, we're going to see some new changes and new focus here. Another thing we're seeing is changes to the building science in attics, right? So traditionally, we had vented attics and they were poorly insulated, probably not very airtight. So there was a fair amount of air leakage and heat driving up into the attic. And in a coastal climate where we have a lot of moisture in our attics, all that heat loss was kind of keeping the attic dry. And as you start to add insulation in the attic and probably reducing air leakage too, that attic, those roof surfaces are getting colder, and so there's more potential for condensation up in the attic. There are some risks there. So what we're seeing people do is stop building these vented attics and starting to make the attic part of the conditioned space, which for you guys as mechanical contractors, all of a sudden there could be some extra space for mechanical equipment that's inside the building envelope. So if you're involved in early design and we're making these decisions, and you could say, well, you know what, I could put some mechanical space up there, and give you back some square footage somewhere else. But if the attic is part of the building enclosure, right? So it's now, a full height room. I think you guys, I'm not going to spend a lot of time talking about windows, but one thing to watch for that we keep hearing is happening is you get architectural plans that you may be using for your heat loss, heat gain calcs, and they will tell you something about the windows, but that's not actually what went in on the building permit. So you have to look at those step code compliance forms that went in with the building permit, because it will list the very, very specific performance specs of those windows. And you want to use those in your heat loss, heat gain calc, because the plans are often for a generic house. And what we're seeing more and more, especially when people want to give themselves lots of choice for mechanicals, is they try to exceed the requirements for the TEDI metrics, so for the envelope. And they do that sometimes by putting in more than one window spec on the house, right? You might have different coatings and glazing on the east side than you have on the south side, than you have on the north side. And so we're seeing a lot of variation. And I've had a number of energy advisors tell me that to please promise that we tell people that if it's not on the compliance report, the step code compliance report, then it's not what's being spec'd for the house, right? And so the building official is checking that compliance form, not the architectural drawings. So just double check that the specs in the compliance form are what you've used for your heat loss, heat gain calc. So the stakes are pretty high when it comes to airtightness, so making sure that you're not going to get blamed and that they've got a strategy is really important, and that you know what material is the air barrier, right? Is it the Tyvek, and what are you doing and who do you need to tell when you make holes, right? Zero carbon step code, optional part of the step code. 9.36.6 is the energy step code, 9.37 is the zero carbon step code. You can look it up. It'll tell you the metrics. What's really confusing about it, if you've seen any of this marketing and branding, they tell you, today we're down here, we have moderate carbon performance, at some point we're going to be at zero carbon performance. And so for me, that makes me think right away, there's no more gas, right, when it comes to the zero carbon step code. Just to be clear, this is optional. Municipalities will tell you what they want you to hit. These are the emission factors that the step code publishes. They say in British Columbia, this is how many kilograms of CO2 equivalent emissions are associated with electricity, so kilowatt hour of electricity, and then a kilowatt hour of natural gas is 18, so about 16 times higher per unit of energy, right? Your heat pump is whatever, 300% efficient, COP of 3 or more. and your natural gas boiler is less than 100% efficient, so you can quickly see how you end up with a lot more emissions associated with heating with natural gas. So renewable natural gas is like, from organic sources, captured from sewage treatment plants and that kind of thing. It is not accepted under the STEP code and the zero carbon STEP code yet. Fortis is lobbying really hard on this, but it's not in there, so it's currently not a calculation option for you. But there's 3 ways of calculating compliance with this. And one of them is to just take the energy use, that MUI calculation that you did that comes out of the energy model, apply the emission factors, and you get a greenhouse gas emission intensity. So the first way, which is really great for small houses, option 1, is just kilograms of CO2 emissions per year for that house. The next one is option 2, you have to comply with both of these. Which is a maximum limit for the house as well as a greenhouse gas intensity per square meter. And the third option is this prescriptive pathway, and this is the one that kind of worries people. So if you don't want to calculate anything because you're not energy modeling, which can still happen, and your municipality says you need to be at zero carbon, it just means there's no fossil fuels on your site. So it's just a checkbox. You don't need to calculate anything, but this is the one that gets you away from fossil fuels quite quickly. 2 examples of homes that have done this. This is an all-electric home in Saanich, 100% electric baseboard heating, step 4 of the STEP code. And so here's your STEP code metrics. This is the requirements for TEDI and ACH. So 28 on their TEDI, ACH of 1.5, a MUI of 48 to hit step 4 in Saanich. And this house, the green boxes are because they way exceeded that TEDI. So their envelope was way better. Their air tightness, they were down at 0.6, which is a passive house level. So they exceeded it. But when it came to the 3 different ways of calculating compliance with the zero carbon STEP code, they met every option. This is what their design metric was calculated at, and this is what they had to hit. So they're, way under their carbon limits at the top step of the STEP code. So, no surprise there. This project is in Nelson, and it's only step 3, so the lowest that we can build today. When you look at their TEDI, the step 3 requirements for this project in Nelson was a 44, TEDI of 44. They just squeaked in an air tightness of 2.5. They were a little bit better than that. A MUI of 43, they're exactly at their MUI, right? It's got a dual fuel furnace, so it's a heat pump with a natural gas backup in the cold climate times. And it was still able to comply with the zero carbon, the top level. So level 4, which is the highest level, it was still able to hit that pathway. It did it through option 2, right? They couldn't hit the total greenhouse gas emissions for the house. They couldn't hit that one. But this one, the intensity with a maximum limit for the house, they were under. And obviously they're still burning gas, so they didn't do that prescriptive option. So you can still use gas. It's only going to get easier as so it's really not very tough. The zero carbon STEP code is not that restrictive. When you're at step 3, you're still kind of needing a lot of heating energy. And that will get easier as you move to step 5, obviously. Yep. There's 3 really important embodied carbon studies right now, and that's what's driving all the municipalities to start putting in place programs and start talking about regulations about embodied carbon. A study in Vancouver of 13 homes. Nelson Castlegar did a study of 34 homes, and there's a huge study in Toronto done of about 500 homes. And they showed massive variations in emissions. This is embodied carbon emissions associated with the envelope, not mechanical, because mechanical is really hard to calculate. So on the worst end of the scale of 500 homes in Toronto, 561 kilograms of CO2 per square meter of built home. On the best end in Toronto, 116. This is kind of your worst. And this is kind of your best, 72. And so there's a huge variation. So if you think about embodied emissions every year are 50% of what we put out linked to buildings. And if we were able to cut that down, 5-fold reduction by choosing, to build differently, that could have a huge impact. So local governments and provincial government really, really interested in this. Where are the hot spots? Concrete is the biggest one up here, insulation choices down here, cladding. And so those are the big ones that are really easy to look at. There is no good data. It's really hard to track this data. And so there is a really good report, and it's from CIBC, so it's British. The building services engineers, it was about heating systems in residential homes. It was designed, they looked at, from multi-unit to smaller townhomes, and they looked at the embodied emissions associated with mechanical systems from their UK office, and now it's gotten a lot of traction. So these guys are shaping policies in Vancouver with a lot of municipalities because they're talking about what do we need to do to make sure we make smart choices as we decarbonize our energy systems, our mechanical systems. This is, when you open the door in your building, this is the potential embodied carbon associated with the mechanical system from the day it's ready to flip the switch and turn it on. So here's a fully gas system, a ground source heat pump system, an air source heat pump system, VRF, fully electric, baseboard heaters and domestic hot water, a domestic hot water heat pump system. The interesting thing is, gas boilers and that kind of thing, gas hot water, are coming in under, in terms of embodied carbon, the heat pumps. And so this is getting attention by municipalities, but what is even scarier is this column here. So these are the same categories in these buildings, categories coming down here, but this category is labeled refrigerant leakage. And so if we start seeing refrigerant leakage from our systems, the life cycle, like as you track this out, this is the day the door opens in the building, then there's occupancy, and then there's decommissioning over the whole life cycle. Refrigerant leakage over here can be huge, and it can really, your gas system stays the same in terms of embodied, but your systems with refrigerant, if we start getting leakage, it blows us way off the chart. So it can potentially send us the wrong direction if we're not really careful. And so the one here that's off the charts that's, I think, 380 is VRF. So, you're already seeing the city of Vancouver starting to crack down on VRF. They don't want to see that. We see a lot of refrigerant leakage in VRF systems in the Lower Mainland, in the corporate downtown core. So it's getting some traction. So stay tuned, because this stuff is going to come out here, and it's going to shape some of the policies and some of the regulations and some of the inspections and certification requirements that are going to come in around heat pumps. So last slide. When it comes to mechanical systems, part of what is driving up embodied carbon in that first chart is metal. So our heat pump systems have more metal, right? We've got outside units as well. So that's part of what's driving up that initial thing. Low global warming potential refrigerants. We're coming out with better and better refrigerants all the time. I say all the time. We're not inventing them every day. They're out there. They're just becoming more. Regulation is switching over to use those. Less refrigerant, that gets us away from VRF systems and other low carbon materials. The STEP code and the zero carbon STEP code are focused on this operational energy. This is a step 5 building, so a high performance building envelope. The day you build it, this is the average from the 30 some homes in the Nelson study, so Nelson and Castlegar. But they took the operating emissions. So, every year you're going to emit a certain amount of CO2 to run that building, and it stacks up every year. But the embodied carbon from the average of those buildings, it takes 23 years in operating emission savings before we hit that embodied carbon number. So At 23 years, we're way past our 2032 timelines. And that's why the focus on embodied carbon. And that's why the focus on making sure we get it right with our mechanical systems. We don't see refrigerant leakage. We're choosing wisely. So this operational side in the box here is what the STEP code, the BC Building Code, and the Zero Carbon STEP Code is focused on. And there's nothing regulating that embodied carbon upfront piece right now. But thank you. So.